Welcome back to the Deep Dive. Today, we're tackling something pretty foundational, but also really complex. We're going deep on data engineering.
That's right. We're moving past the surface level view of data science and looking at the heavy lifting underneath, the engineering that actually makes robust analysis possible.
Yeah, exactly. It's like everyone sees the fancy building, the insights, but we're talking about the foundations, the plumbing, the electrical grid that makes the whole thing stand up and work reliably.
Couldn't have said it better. And our goal here is pretty specific. We're aiming this at two groups, mainly. First, if you're a complete beginner thinking about getting into data engineering.
Okay.
And second, if you're maybe a software engineer already and you're looking to pivot to really understand what's different about building and running data systems in production.
Right. So we want to get you from zero to understanding what a real production-grade data setup looks like.
Precisely. And the key thing to grasp right from the start is that core distinction. Data scientists, they're pulling insights from the data. Data engineers, they're building the reliable, scalable infrastructure that gets the data there, makes it clean, trustworthy, and ready for those scientists. They make the data actually usable.
Without them, the data's just, well, it's often a mess, right? Or inaccessible.
Exactly. A brilliant model fed with garbage data is still garbage. So by the end of this deep dive, you should have a solid grasp on designing pipelines, thinking about quality, governance, applying best practices, especially in the cloud. It's about building that trust.
Building trust in the data itself.
Love it.
Okay, let's start unpacking this. So this ecosystem you mentioned, it sounds like a data engineer juggles a lot of different pieces. It's not just one skill.
Oh, absolutely not. It's managing a whole interconnected system. Think of it like maybe 6 core functions or pillars that all have to work together. If one bit fails, the whole thing can grind to a halt, or worse, start spitting out bad data.
Okay, 6 pillars. Let's break them down. Where does it all start?
It starts with data ingestion. Basically, how do you get the data in the first place? It could be from anywhere, APIs, databases, streaming feeds like Kafka, IoT devices, flat files.
All sorts of sources.
Yeah, very diverse. Then, once you have it, you need data storage. And this isn't trivial. You need to choose the right kind of storage. Is it a traditional relational database like Postgres for transaction integrity? Is it a data warehouse built for analytics? Or maybe just a data lake for dumping raw files?
So ingestion, then storage. What's next? Making it useful.
Exactly. That's data processing. This is where the transformation happens. Cleaning the raw data, maybe joining it with other sources, aggregating it, calculating new features, making it actually usable for analysis.
Okay.
But these processing jobs, they don't just run themselves in isolation. You need data orchestration. Think of tools like Airflow. They manage the schedule, handle dependencies like task B can only run after task A succeeds, manage retries if something fails. It's the conductor of the data pipeline orchestra.
Got it. So ingestion, storage, processing, orchestration, that sounds like a complete flow. What are the last two?
The ones that really separate a hobby project from a production system: data quality and data governance.
Right. Trustworthiness.
Absolutely critical. Data quality is about constantly checking. Is the data accurate? Is it complete? Is it consistent across different systems? You can't just assume it's good. You have to actively monitor it.
And governance, that sounds like rules and permissions.
It is. Data governance covers who can access what data, ensuring security, complying with regulations like GDPR or IPR, keeping audit trails. It's about managing the data as a valuable and sometimes sensitive asset. A production data engineer is constantly thinking about all 6 of these.
Okay, so that's the big picture, the ecosystem.
Yeah.
What are the core tools, the actual hands-on skills needed to work within it? The sources seem unanimous on Python and SQL being central.
They absolutely are. Python's dominance is pretty clear. It's clean. And crucially, the ecosystem of libraries for data work is just massive.
Like what kind of libraries are we talking about day to day?
Well, Pandas is huge. Even if you're working with big data tools later, you're constantly using Pandas for smaller in-memory tasks, quick explorations, cleaning steps, manipulating data on the fly before it hits a bigger system. NumPy is there for any heavy numerical work. Requests is your go-to for pulling data from APIs. And if you're interacting directly with databases from Python, Squillicamy provides a really powerful and safe way to do that, abstracting away some of the database-specific quirks.
Okay, so Python handles a lot of the scripting and interaction. But then there's SQL. You mentioned it's foundational. We're not just talking select from table, are we?
Oh, definitely not. We're talking deep SQL skills. Often the core transformation logic is SQL, especially with modern ELT approaches. You need real mastery.
So what specific SQL skills really matter for a data engineer? Let's maybe pick 3 advanced ones.
Okay, good idea. First, joins. Understanding them inside and out is critical. Not just what an inner join does, but when to use it versus a left join.
Right? Like joining users and orders. An inner join might lose users who haven't ordered anything.
Exactly. A left join keeps all users, showing NLL or 0 for orders, which is often what you actually need for reporting. Understanding the nuances of different join types is fundamental relational thinking.
Okay, joins. What's number 2?
Window functions. These are incredibly powerful. Instead of complex subqueries or self-joins to calculate things like a rank or a running total.
Which can get really slow and messy.
Totally. Window functions let you perform calculations across a set of table rows that are somehow related to the current row, like SERM, sales. Over, partition by region, order by month. You get that running total per region without collapsing all the rows down to one aggregate. It's essential for more complex analytics directly in SQL.
That sounds way more efficient. Okay, third one, CTEs, common table expressions, using the with clause. When your logic gets complex, maybe calculating customer lifetime value involves several steps.
You don't want one giant nested unreadable query. Precisely. CTEs let you break it down. Define step 1 monthly sales, AS, then step 2 customer first purchase, AS, and then finally select. From step 1 monthly sales, join step 2 customer first purchases. It makes the complex logic readable, testable, and much easier to debug. Huge for maintainability.
Okay, Python, advanced SQL. What about the environment? You're not just running this on your laptop, right? Version control and command line.
Non-negotiable. Git is essential. The standard workflow: clone the repo, make a new branch, feature fix ingestion bug, commit your changes logically, push, get a code review. That's how teams collaborate and keep things stable. You need that history and control.
And the command line, the terminal. Feels a bit old school, but still essential.
Absolutely essential. Production systems run on servers, often Linux. You need to be comfortable on the command line. That means using / to connect securely. It means using tools like grep to search through massive log files for errors, maybe awk or sed to quickly parse or transform data in a file without loading it into a big tool.
Right, like quickly checking a huge CSV on the server.
Exactly. Or using cloud CLI tools like the Oz CLI or G-Cloud to manage storage, OS's 3Ls, check job statuses, deploy infrastructure. You can't always rely on a graphical interface. The CLI is often faster and more powerful for operational tasks.
Okay, moving on. We talked about storage as a pillar. Data engineers often design systems using multiple databases, right?
Yeah.
It's not just picking one favorite. Let's start with the classic. Relational databases, like PostgreSQL.
Right. Relational databases are the workhorses. Their defining characteristic is reliability, built on the ACD properties. You remember those?
Atomicity, consistency, isolation, durability. Guarantees about transactions.
Exactly. Atomicity, all or nothing for transactions. Consistency, data always follows the rules. Isolation, concurrent transactions don't mess each other up. Durability, once saved, it stays saved. Plus, they use normalization to structure data logically and reduce redundancy.
So when do you absolutely need that level of strictness?
Anytime data integrity is paramount. Financial systems, obviously.
Yeah.
User accounts, order management, inventory tracking. Anywhere you need strong guarantees about relationships and consistency, especially with complex queries involving lots of joins.
But the world isn't always neat and structured. What about flexibility? That's where NoSQL comes in.
Precisely. NoSQL databases trade some of that ACID strictness for flexibility and often scale. A common type is the document store, like MongoDB. It stores data in flexible JSON-like documents. Great for things where the schema might evolve rapidly, like user profiles, product catalogs with varying attributes, content management.
Okay, so flexibility for evolving data. What if you just need raw speed for simple lookups?
Then you look at key value stores like Redis, often in memory, super fast, perfect for caching data that's frequently accessed, storing user session information, rate-limiting API calls, things where you need millisecond or even sub-millisecond response times for simple key lookups.
Gotcha. Caching, sessions. The sources also mentioned columnar databases. Cassandra was an example. Where do they fit?
Columnar databases like Cassandra are designed for massive scale, particularly write-heavy workloads and high availability. Instead of storing data row by row, they store it column by column. This makes writes very fast and aggregations over specific columns efficient. Think IoT sensor data, logging systems, time series data where you're constantly writing new events.
So it really is about picking the right tool for the specific job within the larger system.
Absolutely. A modern data platform might easily use PostgreSQL for core transactional data, MongoDB for product details, and Redis for session caching. The engineer needs to understand the trade-offs and design that mix.
Okay, we've got our data sources, chosen our storage. Now we need to actually move and process the data. This brings us to ETL and ELT. I hear ELT is the more modern approach. What's the difference?
Yeah, there's been a definite shift. Historically, ETL, extract, transform, load, was dominant. You'd extract the data from the source, do the complex transformation logic on a separate staging server, and then load the clean transformed data into the final data warehouse.
Why did the transformation before loading?
Mostly because older data warehouses weren't that powerful computationally, and storage was expensive. You wanted to minimize the load on the warehouse and only store the clean, necessary data. You pre-processed it.
Does that ETL approach still have a place?
Sometimes, if you have strict compliance needs where sensitive data must be anonymized or altered before it even lands in your main storage, or if you're dealing with really messy legacy systems where the raw data is just too difficult to load directly.
Okay. But now, mostly, it's ELT, extract, load, transform.
Right. This became feasible and usually preferable with the rise of powerful, scalable cloud data warehouses, think Snowflake, BigQuery, Redshift, and cloud storage is cheap. So now you extract the raw data, load it directly into the warehouse or data lake, and then you run the transformation logic using the warehouse's powerful SQL engine.
Ah, so you leverage the warehouse's compute power for the T-step. What's the big advantage there?
Two main things. One, it's often simpler. You might just be doing SQL transformations. Two, and this is huge, you keep the raw data. If your business logic changes later, or you want to calculate a new metric, you don't have to go back and re-ingest everything. The raw data is already there. You just write a new transformation query.
That makes a lot of sense. Flexibility. Now, regardless of ETL or ELT, a pipeline script generally has those three parts, right? Extract, transform, load.
Yeah, the core functions are there. The extract part might use Python with libraries like requests or scopd2 to pull data via API or SQL. The transform part could be a pandas for smaller stuff, or Spark SQL, or just pure SQL in the warehouse doing the cleaning, joining, calculations like, say, adding tax to an order total. And load uses tools to efficiently get the data into the target df.2 SQL for simple cases, or bulk load commands like Redshifts copy-y or BigQuery's load data.
And somewhere in that flow, usually between steps, you need checks, right? Data validation.
Oh, absolutely essential. You cannot skip this. You need checks during the pipeline. Are essential IDs, ordered, customered, present, and not null? Are monetary values positive? Are there unexpected duplicate records showing up? These checks act as guardrails.
What happens if a check fails?
The pipeline should fail immediately and loudly send an alert. You must stop bad data from propagating downstream, because once bad data gets into your core tables, it can corrupt reports, dashboards, ML models, leading to terrible decisions. Garbage in, garbage out has real consequences. Hashtag tag 2.2 workflow orchestration with Apache Airflow.
Okay, so you have these pipelines, maybe lots of them, with validation checks. But how do you manage running them reliably on schedule, handling dependencies? You mentioned orchestration earlier. Simple cron jobs won't cut it at scale, right?
Not even close. Cron just runs a script at a set time. It knows nothing about dependencies, retries, monitoring success or failure beyond a simple exit code, distributing tasks. It breaks down fast when you have more than a couple of simple independent jobs.
So that's where something like Apache Airflow comes in. What does it actually do?
Airflow is designed specifically for orchestrating complex data workflows. It lets you define, schedule, and monitor these pipelines programmatically.
How does it represent a workflow? I hear the term DAG a lot.
Right. The DAG, directed acyclic graph, is the core concept. It's essentially a Python script that defines the structure of your workflow. It lays out all the individual tasks and, crucially, the dependencies between them. Task C depends on A and B finishing successfully. The cyclic part means no circular dependencies are allowed. The workflow has a clear start and end.
And the individual steps within the DAG.
Those are defined by operators. An operator is like a template for a specific type of task. There are operators for running Python functions, Python operator, bash scripts, bash operator, executing SQL, Postgres operator, BigQuery operator, checking for files, S3 key sensor, and many more. You wire these operators together in your DAG file to build the flow.
Okay, DAG defines the structure, operators define the tasks. What actually runs it all?
Two key components. The scheduler and the executor. The scheduler constantly monitors your DAGs, figures out which tasks are ready to run based on their schedule and dependencies, and queues them up. The executor is what actually picks up those queued tasks and runs them. The executor can be simple, running tasks sequentially on the same machine, or complex, like distributing tasks across a Celery or Kubernetes cluster for parallel execution.
When you define a DAG, they're often default targs. What are the important ones for making a pipeline robust in production?
Good question. Beyond basics like owner and start date, you absolutely need robust retry settings. Things like retries 3, try a failed task 3 times, and retry late time delta, wait 5 minutes between retries. Network blips happen. You don't want transient issues to kill your whole pipeline run. You also define the dependencies explicitly using bit shift operators like taska task task or taska taska p task. Clarity is key.
Got it. Retries and clear dependencies. What about more advanced features? How do tasks share information? Like, if my extract task finds a specific file, how does the transform task know which file to process?
That's where XCOM's cross communications come in. Tasks can push small pieces of data, like a file name, a record count, a small JSON payload, to XCOM, and downstream tasks can pull that data. It allows tasks to communicate without relying on external storage for simple metadata exchange. So extract pushes the file path, transform pulls it using the task ID.
Okay, that's clever. What if the pipeline needs to make a decision? Like, if there's no new data, skip the processing steps.
That's branching logic. Airflow has operators like branch Python operator. You write a Python function that checks some condition, e.g. query a database, check an XCOM value for record count, and returns the task ID of the next task to run. So if record count equals 0, it returns skip processing task. Otherwise, it returns run transform task kit. It lets you build dynamic paths in your DAG.
Very cool. And finally, failure. If something goes wrong, especially in the middle of the night, how do you know immediately?
Critical point. Alerting. You configure failure callbacks in your DAG's default arguments or on specific tasks. This is usually a Python function that gets triggered only if a task fails. In production, this function typically does something like sending a message to a specific Slack channel or firing an alert in PagerDuty.
And that message needs context, right?
Absolutely. The alert must include the DAG name, the specific task that failed, the time, and ideally a direct link to the Airflow logs for that task run. That way, the on-call engineer isn't hunting around. They know exactly where to look to start debugging immediately. Fast alerting and diagnosis are crucial for reliability.
Okay, we've orchestrated our pipelines. But as data grows or we need faster insights, just running scheduled pipelines might not be enough.
This leads to thinking about batch versus stream processing, right? Two different ways of handling data flow.
Exactly. They represent fundamentally different approaches. Batch processing is the traditional model we've mostly been discussing. You collect data over a period, an hour, a day, a week, and then process that entire chunk, that batch, all at once on a schedule. What are the typical use cases for batch?
Things like generating daily sales reports, updating a data warehouse overnight, running complex analytical models on historical data, calculating monthly customer summaries. Anything where you need to process a large volume but don't need results instantly.
And the trade-offs.
Batch is generally simpler to implement and manage, often more cost-effective because you're only using compute resources periodically. It's great for throughput processing huge amounts of data efficiently. The big downside, though, is latency. Your insights are always delayed by the batch interval hours or even days old.
Okay, so batch is about volume and efficiency, but it's slow. What's the alternative for speed?
That's stream processing. Here, you process data continuously, event by event, as it arrives, often within milliseconds or seconds. Think of a conveyor belt versus loading a whole truck.
What kind of applications need that real-time speed?
Real-time dashboards showing live user activity. Fraud detection systems that need to block a transaction before it completes. Real-time personalization on websites. Monitoring industrial sensors for immediate alerts. Anything where acting on data now is critical.
And the trade-offs for streaming.
You get that low latency, the immediate insights, but it's generally much more complex to build and operate reliable streaming systems. You have to handle state management, failures, out-of-order data, and often it means higher continuous infrastructure costs because the system is always on, always processing. Hashtag tagged 3.2 scaling batch with Apache Spark.
Let's stick with batch for a moment, but at massive scale. When you're dealing with terabytes or petabytes, single machine processing or even simple database queries aren't enough. This is where Apache Spark becomes essential, right?
Absolutely. Spark is the de facto standard for large-scale distributed batch processing. Its core strength is taking a massive data set and a complex computation, breaking it down, and running it in parallel across a cluster of many machines.
And it's known for speed, too, partly because of memory usage.
Right. Spark tries to perform as much computation in memory as possible, which is much faster than constantly reading and writing to disk like older systems, like MapReduce. It can handle data volumes far exceeding the memory of any single machine by cleverly managing data distribution and spilling to disk when necessary.
Can you walk through what a typical Spark batch job might look like conceptually?
Sure. You'd start by creating a Spark session. Then you'd read your input data, maybe from Parquet files on S3 or HDFS. Spark reads this in parallel into distributed data frames or RDDs. Then you apply your transformations, filtering rows, joining different data sets together, grouping by certain keys, group B, and performing aggregations, like counts, sums, averages.
And the output.
Finally, you write the results out, again off into a distributed file system. A key practice here is partitioning the output data, say by date or region, df.write.partition by date region.parquet.do. This organizes the output file so that future queries that filter by those partition keys can skip reading irrelevant data, making them much faster.
Okay, but running Spark efficiently isn't automatic. What are some key optimization techniques data engineers use to make these large jobs run fast and reliably?
Performance tuning is huge in Spark. One basic technique is caching. If you have a data frame that you need to use multiple times in your job, e.g. you filter it once, then join it twice later, you should .cache or .persist it. Spark will then try to keep it in memory across the cluster, avoiding the cost of recomputing it from scratch each time.
Makes sense. Reuse what you've already computed. What about joins? Joining massive data sets sounds expensive.
It is, especially the shuffle phase, where Spark needs to redistribute data across the network so that rows with the same join key end up on the same machine. This shuffle is often the biggest bottleneck.
How do you minimize that?
One critical technique is the broadcast join. If you're joining a very large table, like billions of transactions, with a much smaller table, like hundreds of store locations, you can broadcast the small table. Spark sends a copy of the entire small table to every single machine in the cluster. Then each machine can perform the join using its local partition of the large table and the full copy of the small table, completely avoiding the massive shuffle of the large table. It can be a game changer for performance.
Wow, okay. Avoid shuffling the big stuff. Any other key optimizations?
Predicate pushdown is another important one, though often handled automatically by Spark in the data source. It means pushing filter conditions, where column of value, down to the data source itself. So if you're reading Parquet files, Spark tells the Parquet reader, only give me rows where date explains 2024-10-26. The reader can then use metadata to skip reading entire files or blocks that don't contain that date, drastically reducing the amount of data Spark even has to load and process. Hashtag tag 3.3 data warehouses, data lakes, and the lakehouse.
So we've processed our data, maybe with Spark. Where does this cleaned, structured, aggregated data ultimately live for analysis? We hear terms like data warehouse, data lake, and now lakehouse.
Right, let's clarify those. The traditional data warehouse, DW, is a central repository of integrated data from various sources, specifically structured and optimized for business intelligence and analytical querying. Key characteristics. It's subject-oriented, for example, focused on customers, products, integrated, time-variant, it keeps historical data, and non-volatile. Data isn't usually deleted, just updated or appended. It uses schema on write, meaning the structure is defined before data is loaded.
Inside the warehouse, how is the data typically structured for good query performance?
The most common and usually recommended approach is dimensional modeling, often using a star schema. You have a central fact table containing quantitative measures like sales amount, units sold, and foreign keys. Surrounding it are dimension tables containing descriptive attributes like customer details, product descriptions, time information. This structure is denormalized compared to transactional databases, which minimizes the number of joins needed for typical analytical queries, making them much faster.
You mentioned warehouses keep historical data. How do they handle changes? Like if a customer's address changes?
That's managed using slowly changing dimensions, SCDs. There are different types, but SCD type 2 is very common for preserving full history. Instead of overwriting the customer's old address, you mark the existing row as inactive. Example, set an end date or its current flag to false, and insert a new row with the updated address and a new start date. This lets you accurately query the data as it was at any point in time. What was this customer's address when they made purchase X?
Okay, so the DW is structured, Historical, optimized for BI. What's the data lake? DL then. Sounds fun.
Huh. Yeah, the idea was a vast repository to store all data in its raw, native format, structured, semi-structured, like JSON, XML, unstructured, like text images. Unlike the DW's schema on write, the DL uses schema on read. You figure out the structure when you query it. It's cheaper for storage, great for flexibility, and often the starting point for data science exploration or training ML models that need raw features, the big danger. Without governance, it can become a data swamp, a messy, unusable mess.
Right, the swamp problem.
Yeah.
So how do you get the structure of the warehouse with the flexibility and scale of the lake? Is that the lakehouse idea?
Exactly. The lakehouse architecture aims to combine the best of both worlds. It tries to bring data warehousing capabilities like ACID transactions, data quality enforcement, schema evolution directly to the data stored in open formats like Parquet on cheap object storage like S3.
How do you organize the data in this lakehouse modern data lake to avoid the swamp?
The best practice that's emerged is the medallion architecture. It structures the lake into distinct quality layers, typically named bronze, silver, and gold.
Okay, break those down. Bronze.
Bronze is the landing zone. Raw data, exactly as it arrived from the source systems. Immutable, untouched, your historical archive. Minimal transformation, maybe just format conversion, like raw logs to Parquet.
Silver.
Silver is where the data gets cleaned, validated, maybe lightly normalized or joined. It conforms to a known schema. Think of it as an enterprise-ready, queryable view of the key business entities. Data scientists or analysts might start working here.
And gold.
Gold tables are highly refined, aggregated, and feature-engineered specifically for business use cases. These are the tables that might directly power BI dashboards or specific analytical applications. They often contain business-level aggregates like monthly revenue by product or customer lifetime value. The transformation logic from silver to gold can be quite complex.
This sounds much more organized. But you mentioned bringing ACID transactions to the lake. How is that possible on just files?
That's the magic of technologies like Delta Lake, Apache Iceberg, or Apache Hudi. Let's focus on Delta Lake as a prominent example. It's an open-source storage layer that sits on top of your existing data lake storage, like S3. It adds a transaction log alongside your data files, which are typically Parquet. This log tracks every change, enabling ACID transactions. Now you can reliably perform update, delete, and merge upsert operations directly on your data lake tables, which was notoriously difficult and unreliable before.
Wow. ACID on the lake.
Yeah.
What else does Delta Lake offer?
Another huge feature is time travel. Because every change is logged, Delta Lake allows you to query the data as it existed at a specific point in time or version number. This is incredible for debugging pipelines. What did the data look like before the bad run? Auditing changes or reproducing reports or ML model results from the past. It brings a level of reliability and governance that was missing from traditional data lakes.
Okay, we've built this sophisticated system, lakehouse, pipelines, orchestration. But it's all worthless if the data itself is wrong, right? The cost of bad data can be huge.
Absolutely catastrophic. Incorrect run reports lead to bad decisions. Flawed data fed into ML models leads to poor predictions. It erodes trust across the entire organization. Data quality isn't a nice to have. It's fundamental to the value proposition of data engineering.
So how do we systematically ensure quality? Are there specific dimensions to look at?
Yes, there's a commonly accepted set of 6 dimensions of data quality. 1, accuracy. Does the data correctly reflect the real-world fact? 2, completeness. Are there missing values where there shouldn't be? 3, consistency. Is the same data represented consistently across different systems or tables? 4, timeliness. Is the data available when it's needed? Is it acceptably up to date? 5, validity. Does the data conform to the defined format, type, and range constraints? Shiji, is an email address actually an email format? 6, uniqueness. Are there duplicate records that shouldn't exist, e.g., duplicate customer IDs?
That's a comprehensive checklist. How do you actually implement checks for these dimensions in a pipeline? Manually write lots of validation code.
You can, but it gets tedious and hard to manage. That's why frameworks like Great Expectations have become so popular. It provides a structured way to define these quality checks or expectations in a declarative way, often in JSON or Python.
Can you give an example?
Sure. You might define an expectation like expect column values to not be null, usered, or expect column values to be new or ordered, or more complex ones like expect column in between transaction amount min value 5.0, max value 1000.0, or even expect column values to move regex, email addresses, regex plus @days plus plus.
And Great Expectations runs these checks against your data.
Yes, typically as a step in your pipeline, often using Airflow operators designed for it, it validates the data against the defined expectations and produces a detailed report. Crucially, it can be configured to fail the pipeline run if critical expectations aren't met, preventing bad data from moving forward.
Beyond frameworks like Great Expectations, are there other custom checks engineers implement?
Definitely. You often need custom checks for things like referential integrity. For example, does every order.customer exist in the customer's table? Data freshness, e.g. is the loaded today actually, from today, not stale, or statistical anomaly detection, for example, using z-scores or other methods to flag unusual spikes or dips in key metrics that might indicate a problem.
Okay, so testing the data is vital. What about testing the pipeline code itself?
Equally important, just like software engineering, data pipelines need testing. We
Hmm,
typically use, one, unit testing, using frameworks like PyTest in Python to test individual functions, especially transformation logic. Does my calculate tax, price, rate function return the correct value for known inputs? Does cleanmail email string handle weird edge cases correctly? Two, integration testing. Testing how different components of the pipeline work together. This often involves running a small version of the pipeline against a dedicated test database with sample data, then verifying that the output data in the target tables matches the expected results, correct schema, correct counts, correct aggregations.
makes sense. Test the parts, then test them together. I also saw idempotency mentioned as a key testing concept. What's that about?
Ah, idempotency is crucial for reliability, especially with retries. An idempotent operation is one that has the same effect whether it's executed once or multiple times. For a data pipeline, this means if the pipeline runs successfully, and then due to some orchestrator issue, it accidentally runs again with the exact same input data, the final state of the target database should be identical to after the first successful run.
So it shouldn't insert duplicate records or double count metrics on a retry.
Exactly. You test for this by running the pipeline, checking the state, then running it again immediately, and asserting that the state hasn't changed unexpectedly. Designing pipelines to be idempotent, example, using merge upsert logic instead of simple insert, or checking for existing records before inserting, is vital for building fault-tolerant systems.
Reliability is key, but so is speed. Data needs to be available quickly for analysis. Data engineers spend a lot of time on performance tuning, especially database queries, right? Indexing seems like a big part of that.
Huge part. Indexes are data structures that allow the database to find rows matching specific query conditions much faster, avoiding a full table scan. Basic B-tree indexes on single columns are common. Composite indexes on multiple columns are important for queries filtering on several fields.
Any advanced indexing strategies?
One really powerful technique is the covering index. This is an index that includes all the columns needed to satisfy a specific query, both the columns in the where clause and the columns being selected. If a query can be answered entirely using just the index, the database doesn't even need to access the main table data pages. This can lead to massive performance gains for frequent, critical queries by minimizing I/O.
Beyond indexing, sometimes the way a query is written is just inefficient. What about query rewriting?
Yes, sometimes seemingly small changes in SQL syntax can have a big impact on how the database optimizer executes the query. A classic example is avoiding functions on indexed columns in the where clause. Writing where date timestamp call 2024-1026 often prevents the index on timestamp call from being used. Rewriting it as where timestamp call equals 2024-1026-000000 and timestamp call 2024-1027-00.0.00 allows the index to be used effectively.
Any other common rewrites?
Replacing OR conditions with union all sometimes helps the optimizer. Using exists or left join is null instead of not in with subqueries is often much faster, as we discussed. Understanding the database's execution plan, explain command, is key to identifying these bottlenecks and figuring out how to rewrite for better performance.
What about optimizing the data structure itself?
Absolutely. Partitioning tables, especially large fact tables in a data warehouse, is a standard technique. You physically divide the table data based on a key, oftentimes, e.g. partition by month or year, or sometimes region or category. When queries filter on the partition key, the database only needs to scan the relevant partitions, dramatically reducing the amount of data read.
And materialized views.
MVs are great for pre-computing the results of expensive, frequently run aggregation queries. Instead of recalculating, say, total monthly sales by region every time someone queries a dashboard, you run that calculation once, maybe daily or hourly, and store the results in a materialized view. Queries then hit this pre-computed table, which is lightning fast. The trade-off is storage space and ensuring the MV is refreshed appropriately.
And for Spark jobs, any common performance pitfalls to avoid?
A big one is accidentally collecting a massive data frame to the driver node. The driver usually has limited memory, and trying to pull terabytes of data back to it will crash the job. Also, using Python user-defined functions, UDFs, can be slow because Spark has to serialize data back and forth to the Python process. Whenever possible, stick to Spark's built-in functions, which run much more efficiently within the JVM. Hashtag tags tag tag 4.3 Cloud Native Data Engineering, a quick tour.
It feels like almost all modern data engineering happens in the cloud now. Let's do a quick tour of some key services on the major platforms, starting with AWS. What are the essentials there?
AWS is huge in the data space. The foundation is S3, simple storage service. It's incredibly scalable, durable, cost-effective object storage, a backbone of most AWS data lakes. Engineers use features like lifecycle policies extensively to automatically move older, less frequently accessed data to cheaper storage tiers like S3 Glacier to manage costs.
Okay, S3 for storage. What about processing like ETL?
AWS Glue is their serverless ETL service. It provides a data catalog to store metadata about your schemas and can run Spark ETL jobs without you needing to manage any servers. It integrates tightly with S3 and various databases. For a dedicated data warehouse, Redshift is there offering a columnar petabyte scale warehouse. A key performance feature there is the copy-y command, which allows highly parallelized bulk loading directly from S3, much faster than single inserts.
Any other key AWS services for data engineers?
AWS Lambda is often used for lightweight event-driven processing. For example, a Lambda function could trigger automatically when a new file lands in S3, perform a quick validation check, and then maybe kick off a larger Glue job or send a notification. It's great for gluing services together.
Moving over to GCP, Google Cloud. What are the counterparts?
GCP's flagship data warehouse is BigQuery. It's fully serverless, scales massively, and has a pay-per-query pricing model that can be very attractive. It's known for its speed on huge datasets. Engineers often use features like parameterized queries for security and reusability when building applications on top of it. For data processing pipelines, both batch and stream, Dataflow is their managed service for Apache Beam, offering a unified programming model.
So similar capabilities, different names and approaches. Regardless of the cloud provider, how do teams manage deploying and updating all this infrastructure reliably? Clicking around in the console seems risky.
Very risky and not repeatable. That's where infrastructure as code, IAC, comes in. Well, tools like Terraform or cloud-specific ones like AWS CloudFormation or GCP Cloud Deployment Manager are the standard. You define your entire infrastructure, S3 buckets, Glue jobs, Redshift clusters, IAM permissions, network settings, and configuration files.
And then Terraform figures out how to create or update the actual resources.
Exactly. You run Terraform apply, and it makes the cloud environment match your code. This makes deployments repeatable, version-controlled, you check your Terraform code into Git, and much less error-prone. It's essential for managing complex production environments securely and consistently across dev, staging, and prod.
Wow. Okay. We've covered a ton.
Yeah.
From the basics of Python and SQL, through building and orchestrating pipelines with ETL, ELT, and Airflow, scaling with Spark, choosing the right storage like warehouses and lakehouses with Delta Lake, and ensuring quality performance and managing it all with IAC in the cloud.
It's a big landscape. But if you master these areas, you're well on your way to being a proficient data engineer. However, there's sort of a final frontier, the area where the engineering challenges get really intense. And that's true real-time processing.
Handling data not in batches, but millisecond by millisecond.
Precisely. Moving beyond near real-time updates to systems that react and make decisions based on events as they happen. This is where the ultimate test of production engineering lies.
Didn't that used to involve really complex architectures? I remember hearing about the Lambda architecture.
It did. Lambda was an early approach that essentially required maintaining two separate pipelines. A slow, reliable batch layer for accurate historical data, and a fast, approximate speed layer for real-time insights. You had to manage two code bases, two systems, and then merge the results. It was complex and operationally burdensome.
So what's the modern approach?
The trend is towards the Kappa architecture. The idea here is to simplify things by having only a stream processing layer. You treat everything as a stream. If you need to recompute historical results or fix an error, you simply replay the stream from an earlier point through your single stream processing pipeline. Technologies like Kafka with long retention periods and powerful stream processors make this feasible now. It drastically simplifies the architecture.
Speaking of Kafka, when you're building these critical streaming systems, what kind of rigor is needed to ensure you don't lose data or process things incorrectly?
The guarantees become paramount. You hear a lot about exactly once semantics, EOS. While true EOS across distributed systems is complex, the goal is to ensure that each event is processed effectively once, even if failures and retries occur.
How do you achieve that practically?
On the consumer side, reading from Kafka, it often means disabling auto-commit of offsets and manually committing the offset back to Kafka only after the processed result has been successfully stored downstream. On the producer side, writing to Kafka, it involves using settings like AX, all, wait for all replicas to acknowledge the write, and configuring retries carefully, potentially with an idempotent producer, to avoid data loss and duplication during network issues.
And using this streaming power for something like fraud detection, how's that work?
That's where stateful stream processing comes in, using tools like Apache Flink or libraries like Faust in Python. These tools allow your processing logic to maintain state across events. For fraud detection, you might key the stream by userid. The processor keeps track of recent activity for each user, e.g. transaction count, and timestamps within the last minute.
So it remembers what happened just before.
Exactly. It can then detect complex patterns in real time. For instance, if a fraud detector function sees more than, say, 5 transactions from the same user within a 1-second window, it can immediately emit a fraud alert downstream. It's maintaining and querying state on the fly across millions of events.
That's incredible, making complex decisions in sub-seconds based on patterns in the flow.
That's the end game. The journey in data engineering culminates not just in building systems that move data reliably, but building systems you trust enough to make automated, high-impact decisions in real time. So the challenge for you as you learn and build isn't just, can I build a pipeline? It's, can I build a pipeline that monitors itself, potentially heals itself, and processes critical events faster than the real world can change?
A powerful closing thought. So the question for everyone listening is, where in your world, your projects, your systems, does that sub-second reliability and real-time decision-making actually matter? Because that's where this kind of engineering truly changes the game.
Absolutely. And that feels like a good place to wrap up this deep dive.
Agreed. Thanks for sharing all that insight. And thank you for tuning in. Until next time on The Deep Dive.